Now with Q3047 turned off and Q3034 turned off, we need a current path, so catching diode CR3045 comes into conduction to complete the current path. Now at a time dictated by U3105, pin 9 will go low, turns off Q3102, releases the short on T3030. Now the direction of current in that series circuit now is such that it will turn on Q3034. Now that short will be removed and Q3034 will turn on during the third quadrant of your sine wave. It'll remain on now during the fourth quadrant. Now just as soon as zero crossing occurs again, we get that same differentiated pulse into U3105, which turns on Q3102, places a short on the transformer T3030, turns off Q3034. Now the current will have reverse direction again, you see, at zero crossing. CR3034 comes into conduction to provide a current path, while Q3034 and Q3047 are off. Now just as soon as the short is removed from the transformer, then Q3047 will turn on and we've begun the second cycle. Now the oscillator will operate at a frequency always below the natural resonant frequency of L3037 and C3037. Now we said that the voltage applied across this entire series circuit, composed of that resonant network and the primary of T3101, would be a square wave of 330 volts. Now an AC divider is formed, composed of the series resonant circuit and the primary of T3101, such that about 95 volts of AC signal appears across the primary of the transformer. The balance appears across the series resonant network. Now if the input line voltage increases, we will sense that increase in the regulator IC U3105, increase the time in which the short appears on T3030, thereby reducing the frequency of the oscillator. The oscillator, therefore, is operating farther away from the resonant frequency of L3037 and C3037. The impedance of that network increases, therefore, and the voltage drop across it increases, maintaining a constant voltage drop across the primary of T3101. Now, since that voltage is constant and the current is constant, then the rectified supplies in the secondary are constant. Now, if something happens to the regulator, then the supply could run wild, in which case we want to shut down the oscillator. Voltage drop across T3101 primary runs at about 95 volts. Now with each positive half cycle at the top of that transformer, CR3057 turns on and places a charge on C3049. Or perhaps I should say reestablishes the portion of the charge that will have leaked off through R3049 between cycles. Now if the oscillator starts to run wild, and the voltage drop across the primary of that transformer gets up to about 110 volts, then we will charge C3049 to that value. We'll lift through Zener VR3059, lifting the gate of Q3052. That SCR will fire. Now the cathode will come up and the anode will come down. Let's take the cathode first. That positive step to the left into the base of Q3048, turns that transistor on and saturates it, places a short right across that 4-turn secondary of the transformer, and stops the oscillator. Now, that could occur at any portion of the cycle, and it could possibly blow a transistor, but this is an emergency situation. The CRT anode supply is derived from this pre-regulated supply. If this supply goes too high, then the anode supply for the CRT goes too high, and we're in danger of exceeding the X-ray limits set by the government. So it's important that we shut down the supply, even if it means blowing a transistor in the process. Now we want the oscillator to stay off for a period of time before trying to turn on again. So back to the SCR, as the anode pulls down through CR 3050, discharging and holding discharged C3048. Now as soon as the oscillator stops, we then allow C3049 to discharge through R3049. As soon as it's succeeded in discharging, then the SCR resets. That in turn turns off CR3050, allowing the start circuit to begin to come on. In the meantime, C3049 is charged up through R3034 to the positive side of the rectified supply. Just as soon as C3048 has taken on its 32-volt charge, CR3040 will fire and start the oscillator again. Now, if the regulator still isn't working, it'll shut down once again, provided, of course, you haven't blown a transistor in the process. But this shutdown circuit prevents the CRT anode potential from getting high enough to cause dangerous X-ray radiation. Now, at the time that Q3052, the SCR, fires, then C3050 provides current through that SCR to drive the base of Q3048 into saturation to shut down the oscillator. Now look down to the left of T3101. Notice the little RC network there. R3039 grounds the cover, which covers this inverter circuit. C3039 couples any currents that might capacitively couple into the cover right back into the inverter circuit. Now off to the left of T3030, C3030 couples any currents that might be capacitively coupled into that secondary winding, couples them back into the inverter circuit. See, it's important that all of the currents be contained within the inverter circuit and not get into the chassis. Well, the diodes in series with the bases of the oscillator transistors, let's take the top one, CR3032, makes it easier to turn those transistors off at the time of zero crossing. Well, let's look now at the regulator IC, U3105. That's a TechMate IC. Now to the right of it, the bridge rectifier provides a 7.5 volts and a -2 volt supply for the IC. Now the current return for that supply is down below there through those three diodes, CR31, 38, 39, and 40, and through R31, 37 to ground. Now we have three sense inputs. Pin 13 will sense an excessive current in the inverter. Notice it's labeled I sense. Pin 15, which is labeled E sense, senses any change in the 54 volt output from this supply. That's just a more positive supply and is used to sense the output from the entire inverter supply. Then pin 2 is labeled balance sense and will sense a change in either direction from the +5 volt lamp supply or the -17 volt supply. Now to better understand the operation of this regulator, if you'll draw on your scratch paper a comparator composed of two NPN transistors. We're going to oversimplify this, of course. Return the common emitters to, well, just an emitter supply. Tie the left collector to a plus supply. The collector of the right transistor has a collector load resistor, and that takeoff goes through an emitter follower to pin 9. Also tied to pin 9 is that latch that we mentioned a moment ago. Now the base of the right-hand transistor is tied to pin 12. It's labeled monostable ramp. Now at the time of zero crossing, when that positive going differentiated pulse comes in at pin 10 or pin 11 of the IC, and we said that caused pin 9 to go high, at the same time it releases a hold down at pin 12, and C3150 begins to ramp up towards 7.5 volts. Now that positive going ramp appears at the base of the right transistor in your comparator sketch. Pin 15, the E sense, is tied to the base of the left transistor. Now a sample of the 54 volts supply appears at pin 15 and the base of that transistor, setting a DC level. Now as the ramp begins to run up on the base of the right transistor, soon comparison will be made with the level from pin 15. When that happens, it turns on the right transistor in the comparator, the collector comes down, and that low at pin 9 of the IC turns off Q3102, releasing the short on transformer T3030 and allowing Q3034 or Q3047, the oscillator transistors, to turn on again. Now, if we increase the line voltage, then the 54 volt sample would go more positive. Pin 15 would go more positive. The base of the left transistor in your sketch goes more positive. The ramp on the base of the right transistor would have farther to go before comparison is reached, a longer period of time before the right transistor turns on and removes the short from transformer T3030. With a longer off period, we've reduced the frequency of the oscillator. It's now operating at a frequency farther away from the resonance of L3037 and C3037. The impedance of that series resonant network increases. We increase the AC voltage drop across that series resonant network, maintaining a constant AC drop across the primary of the transformer and maintaining a constant output from the rectified supplies. Let's look more closely at the E-sense divider composed of R3142, the 54 volt adjustment, that's just a regulator adjustment, R3143, there's R3144, R3146, and VR3147 to ground. Now R3147 to minus 17 volts just provides keep alive current for that zener.
Okay.
Now CR3144 is reverse biased under normal operating conditions. However, if we lose the minus 17 volt supplies, then CR3144 comes into conduction, retains that E-sense divider, and keeps the regulator from running wild. Now let's look at I-sense there at pin 13. If the current in the inverter increases, then we get a greater voltage drop across R3137, which pulls down on pin 13 and influences the regulator. We'll see that in a moment. Pin 2 is rather obvious, just a simple divider tied between 5 volts and minus 17 volts. It's important to realize, however, that that's a bilateral control and will influence regulation if it goes in either direction. Now let's go back to that comparator that you sketched a moment ago. On the left side of the comparator, sketch 2 more transistors. Now that's on the left side. Tie the emitters together. Tie the 3 collectors together. One of the bases tie to pin 13 through an inverter. Remember, we said that an increased current would pull down on that point, so we need an inverter in the line. Tie the 3rd base to pin 2. Now, under normal operating conditions, the base tied to pin 15 of the IC is the more positive base. It exercises control over the regulator. Now, if, however, an increased inverter current is felt, such that it begins to pull down on pin 13 of the IC, inverted then, lifts the base of the transistor tied into pin 13, lifting that above pin 15, then the I-sense takes over control. If, on the other hand, an imbalance is felt in at pin 2, that will lift the base of the transistor tied to pin 2, and it will assume control. So, normally pin 15 has control with the E-sense. I-sense and balance sense assumes control only when an extreme load occurs. Now, please understand that I've oversimplified this IC. I'm sure that you realize that we have quite a bit of circuitry between pin 2 and the base of that 3rd transistor in our little sketch, so that it reacts to both a plus and minus error voltage at that point. The result, an increase in the voltage at the base of a 3rd transistor in our sketch. Now, if an extra large current is felt at pin 13, that would be as a result of a shorted winding in a transformer, shorted filter in the secondary of the supply, or something of that sort. Then we want to shut down the oscillator. The same is true if we sense an extraordinary change at pin 2. That will shut down the oscillator. Also, if the line sense fails at pin 4, that is, we've shut off the instrument or lost power some other way, that will shut down the oscillator. So there are 3 ways that this control IC can stop the oscillator. Now let's take the line stop in at pin 4. Now, as long as sine waves are received from transformer T3001, we keep turning on a transistor inside of the IC. Its collector is tied to pin 3, and as that transistor turns on, it continually discharges C3117. Now, as soon as we lose power, turn the power switch off or some such, then C3117 begins to ramp up. It only needs to go 600 or 700 millivolts, and that begins the shutdown procedure. The same procedure can be initiated, as we said, by a radical change in pin 13 or pin 2. Now, when pin 13 or pin 2 signal a shutdown, then pin 1 on the capacitor, C3114, has to charge up to 600 millivolts. The pull-up is inside of the IC, and there's a 10 millisecond delay before shutdown is initiated. At that time, pin 8 is pulled up, or rather it's just released. That's the collector of a transistor, which turns off, which allows pin 8 to pull up. Now, prior to this time, the collector supply for Q3102 and Q3104 was a full-wave rectifier composed of CR3101 and CR3102. It's tied up to the transformer T3030, of course. Now that pulls up through CR3106 and CR3108 and places a charge on C3106 and C3108. Just as soon as the pull-down is removed at pin 8, it begins to move up as it charges C3113. It then turns on Q3104. As the emitter pulls up, it turns on Q3102. That transistor doesn't saturate, but its collector comes down, pulling down on CR3101 and CR3102, placing a short on T3030 and stops the oscillator. In the meantime, as Q3102 and Q3104 collector pull down, it disconnects CR3106 and CR3108, leaving the charge on C3106 and C3108. Now that charge must leak off through saturated Q3104 before Q3104 can turn off. That in turn turns off Q3102, releases the pull down, and the oscillator can start again. However, it must use the startup circuit composed of CR3040, C3048, and so on to start the oscillator once again. So at the time that shutdown is signaled, there's a 10 millisecond delay before shutdown is initiated. Then shutdown lasts for 250 milliseconds, dictated by the RC time constants in the base of Q3104, at which time the oscillator can start again. If the overload is sensed once again, there's a 10 millisecond delay, and the oscillator is stopped again. So under an overload condition in which we want to shut down the oscillator is on for 10 milliseconds and off for 250 milliseconds. And that rather low duty cycle prevents damage to any of the circuits. Now the idea of the 10 millisecond delay in initiating shutdown is to mask an increased current requirement at the time of initial turn on, as the capacitors around the circuit are charging. Now during that time we will sense an overload, but the 10 milliseconds gives the oscillator a chance to start charging those capacitors. Now that overload will shut down the oscillator 2 or 3 times during initial warm-up, but each of those 10 millisecond periods allows the capacitors to take on some charge. Now the two time constants in the base of Q3104, the left one there, which is a fast time constant, provides the current necessary to turn on and saturate Q3104 initially, and then the other time constant, C3108 or 3111, is a longer time constant and provides the 250 millisecond off time. To the left is a catcher network composed of CR3103, VR3105, a 15-volt Zener, and C3105. Well, that's to limit a ringing that occurs as Q3102 turns off. There's an inductive kick out of that transformer which would cause a ringing. It is caught and suppressed as CR3103 and VR3105 turn on, connecting C3105 across the secondary of that transformer T3030 and suppresses that ringing. The rectifiers in the secondary of the supply are very straightforward, just full-wave rectifiers with rather conventional filters. Notice the takeoff, which goes to T4201 over on the CRT circuit. Now, T4201 is another transformer which supplies the CRT heater, the post-accelerating anode, CRT cathode, and also drives a bridge rectifier over there which supplies 150 volts to the CRT circuit, and also lights the graticule lights. Well, that completes the inverter and the instrument. This has been a detailed circuit description of the Tektronix 7704A oscilloscope. This has been Chuck Miller.